All right, so this video is on Hess's law and the last two ways to calculate the enthalpy of a reaction, the delta H of a reaction. Okay, we talked previously how there are 5 different ways. The very fifth way we're not learning during this unit because it goes along with bonding, and I want to review Lewis structures before I show you how to do that. These are the last 2 ways, Hess's law and from the enthalpies of formation, which is dubbed the Big Mama equation. Okay? Alrighty. Number 21. This is the beginning of Hess's law. I know your packet doesn't have page numbers, but it's like, I think, the 7th page. Number 21. My board here has typos. Your packet is fine, but let me fix those typos real quick. There should be a 1/2 in front of this and a 1/2 in front of this. Okay. Hess's law. It kind of utilizes the idea from when we were balancing redox and doing anionic equations back in Unit 2, when we were canceling things out that cancel, or they're the same on both sides, and adding things together that are on the same side together, things like that. So we have this goal equation. We're given the enthalpy change for these 2 reactions, here and here, and then we want to calculate the enthalpy change for this reaction. This reaction here is what I'm going to call the goal equation, or the goal reaction. We need to manipulate the 2 given reactions so that they form this overall goal equation. And the way we're going to do that is by looking at the substances that are in the goal equation and maybe flipping a reaction, multiplying it, dividing it, stuff like that. States of matter matter. States of matter are important. Because say like this is carbon dioxide in the gas form, say up here this was carbon dioxide in the liquid form. They would not be the same thing. Okay, the states of matter have to match in order for you to cancel or to add together, okay? So, we're going to look at our goal equation and notice that we have carbon monoxide, right? CO is carbon monoxide. We're going to look at the equations given and see which equation is carbon monoxide in, or is it in both? So, ask yourself, so start with your goal equation. So carbon monoxide, is it found in only one of our equations that we're using? Yes, it's only found in the first one, right here. Is it on the correct side of the arrow that we need it for our goal equation? No. So in order to make it be on the correct side, what are we going to do to that first reaction? We're going to flip it. Make the products reactants, make the reactants products. Does my carbon monoxide have the correct coefficient as the goal equation? I don't know if that actually does anything covering the microphone. I like to think it does. So yes, it has the correct coefficient, so we don't need to multiply it or divide it. We just have to flip the reaction. So when we flip this first reaction, carbon monoxide is now my reactant, and it's decomposing into carbon in the solid form and 1/2 oxygen in the gas form. So this reaction here is the synthesis or the formation of carbon monoxide. And it has a delta H value of negative 111 kilojoules. If I flipped it, now I'm decomposing carbon monoxide. What is that delta H value? Positive 111 kilojoules. Opposite processes have the same value but opposite signs. Okay, so if you flip the reaction, you flip the sign on the delta H. And I think we saw a problem like that a while ago in this unit. Speaking of, though, what does that little degree sign mean? That means that this reaction is occurring at standard conditions, or STP, right? Standard temperature and pressure. So what's standard pressure? One, one atmosphere. What is standard temperature? So, no, no. So here's where it can get a little frustrating with chemistry. Um, gas laws, STP is 0 Celsius and 1 atmosphere. For thermo, and for a lot of other things, STP is 1 atmosphere. That's still the same, but 25 Celsius. Because it's at room temperature. Yeah. Yeah, or 298 Kelvin. So, like on your AP exam, it actually has like a disclaimer that unless otherwise stated, assume everything's happening at 25 Celsius and 1 atmosphere. Okay? For right now, eventually later in a later unit, we will talk about how to compensate when we're not at standard conditions for like this thermo stuff and other things. We're not there yet. Let's just learn the basics for right now. I just wanted to go over what that degree sign meant. You're not going to deal with something that's not at standard yet. You will eventually. Okay? Yes, PV does equal nRT, but that has nothing to do with our problem we're doing right now. Okay. But I'm glad you know that formula. All right. So, I just did it non-ironically that time. That was an accident. O2. O2 is the next thing. So we've taken care of the carbon monoxide. We've put it on the correct side from our reactions that we're manipulating, and it has the correct coefficient. So we're done with carbon monoxide, or we should be. O2. Is it found in only one of our reactions? No, it's found in both. For things that are found in multiple equations, skip over them. Deal with the things that are only found in one reaction first. Because hopefully, if you fix the things that are found in only one reaction, the things that are found in multiple end up working out on their own. And that often is the case. So we're going to skip over O2, and we're going to go straight to CO2. Is it found in only one equation? Yes. CO2? We're beyond the goal equation. Yeah, it's only, we're looking up here. It's only found in one equation, and that's this one. Right? Is it on the correct side of the equation? Yes, it's a product here, and it needs to be a product for our goal. Does it have the correct coefficient? Yep. So we're not going to do anything to this second equation. We're just going to rewrite it down here. So that delta H did not change. It is still negative 394 kilojoules. Okay, so that took care of CO2. So now we're going to just add the reactions together. And everything that's on the left side stays on the left side. Everything that's on the right side goes on the right side. But we're going to cancel things that can cancel. So things that are the exact same on both sides are going to cancel out. Kind of like what we did with our spectator ions. And our electrons when we were balancing redox. Right? So this carbon, notice that it's net, like we get it out as in the first reaction, and then we use it in the second one. It's a product, then a reactant. So it's going to cancel out. Our net is that we don't use it at all, right? So that cancels. Now in the, so the carbon monoxide, that's going to come down. It's not going to change. O2. We want 1/2 O2 on the left based on the goal equation. Does that occur? Yes, because we are producing 1/2 O2 here, and we're using a full O2. Think about it this way. You put in 1, you get out half, so the net is putting in half, right? So 1/2 O2 gas. And then CO2 doesn't cancel with anything. Adding up your your equations to get to the goal equation is helpful for making sure that you did manipulate them properly. If when you get to this point and something didn't cancel that was supposed to cancel, or maybe something isn't the correct coefficient, or whatever, then you've done something wrong. Don't do anything more with your delta H's. Try to figure out where you went wrong. So when you add these together, you should get the goal equation. If this equals your goal equation, then you're good to proceed in calculating delta H for this reaction. And the way you're going to do that is by adding up the delta H's after they've been manipulated. Okay? So we're going to take 111, positive 111, and add it to negative 394. Yes, what was your question? Oh, yeah, they can both be negative. Yeah. Yeah, because the question is, what is the enthalpy change for this reaction? So our final answer is the delta H for this reaction that we wrote here. So what is 111 plus negative 394? That's kilojoules. So that is the answer, which is why I circled it. Writing out this reaction and doing this work is just to make sure that you're manipulating the delta H's given properly. Okay? Questions on that? Don't worry, we have another one to do. Number 22.
When you're considering sig figs, does that count as negative? Does that count as a constant? Like something that you don't really consider?
Technically, these are constants, but you can still do sig figs with them. So remember, when you're adding and subtracting, you're looking at least, like you're looking at place value. So with the last one, it didn't really matter because these were both whole numbers, so we want our answer to be to a whole number. It's actually the fact that we had words are not coming out properly. The fact that we listed as negative 283, we weren't using 3 sig figs. We were using significant figures to the ones place. It just happens to also be 3 sig figs. So for this one, when we manipulate and stuff like that, we'll need it to probably the whole number. But we're going to do a little bit more manipulation with this one than we did with the last one. So we have these 3 equations that need to add up through some manipulation to our goal equation. What is our goal equation?
C2H6 plus some amount of oxygen equals CO2 plus H2O.
How do you know that? Yeah, it's the combustion of ethane, which I gave you as C2H6. So sometimes you're not given the goal equation written out explicitly. Sometimes you're given extra information to then write the goal equation, like we did here. You should know that combustion reaction is the reaction of some substance, in this case ethane, with oxygen gas. The products being carbon dioxide and water. So as you're writing your goal equation, you can kind of use these substances to tell you what the states of matter are going to be. For example, C2H6, if you're looking at all these equations that we're going to be using, C2H6 is in the gas state. So we will have C2H6 gaseous. Plus, what is it reacting with? O2, which we know to be a gas, forming CO2, which is a gas, and H2O, which is a liquid because that's what's listed here. Some combustion reactions, that water is going to be the liquid phase, some of it's going to be in the gas phase. It really depends on the reaction, okay? So use your context clues to figure it out. What do we need to do with this? Balance it. So I'm going to pause while you guys take a moment to balance this. The coefficients when this is balanced are what? 2746, except for the fact that we needed to balance this for 1 mole of ethane. So when this happens, you didn't do anything wrong yet. Not yet, at least. You need to have a 1 in front of the C2H6 because we need this for 1 mole of ethane. So what are we going to do to all of our coefficients? Divide by 2. So what are you going to have in front of O2? 3.5, or in fractional form, 7 halves. What's going to be in front of CO2? 2. And in front of H2O? 3. Back in first year chem, you may or may not have ever been told that you can actually use fractional coefficients. It's not wrong to do that. But oftentimes at the first year chem level, we're just trying to make sure you understand how to balance. So we're like, just do whole numbers because then we don't have to deal with the fractions. Oftentimes with these combustion reactions and with thermo, you want to be dealing with like 1 mole of your hydrocarbon, which often will put a fractional coefficient in front of O2. That's perfectly okay. But because we want to know the heat of combustion for 1 mole of this, we need to have a 1 in front of C2H6. Got it? All right. So now we're ready to start manipulating the equations. Let's start off with the first thing in our equation, the C2H6. Is it found in only one reaction that we're going to be manipulating? Yep. It's found in which one? The first one. It's right here. So is that on the correct side? Nope. Does it have the correct coefficient? Yep. So what are we going to do to it? Flip it. And only flip it. So C2H6 is my reactant, and it's the decomposition. What is that delta H value now? Positive 84.68. Next one, O2. So we dealt with the C2H6. O2. Is it found in only one equation? No. So let's skip over that. Hopefully it works out on its own, right? So on to CO2. Is it found in only one equation? Yes. Which one? The second one. It's found right here. Is that the correct side? Yep. It's a product in our goal. It's a product in this equation. So we don't need to flip it. Does it have the correct coefficient? No. What coefficient does it need? 2. So how are we going to, what are we going to do? We're going to multiply the entire equation by 2. So this becomes 2C solid plus 2O2 gas, forming 2CO2 gas. So this delta H, the negative 394 kilojoules, is for one of these reactions. If we multiplied them all by 2, what are we going to do to that delta H? Multiply it by 2 as well. Whatever you do to the reaction, you need to do to the delta H. So our delta H for this reaction will be what? Negative 788. Good. And then the last, so that was carbon dioxide. We took care of that. So now we have to deal with the waters. Is it found in only one equation? Yep. It's found in the third one, and only the third one. On the right side? Or the correct side, I should say? Yep. Coefficient? No. So what do we need to do to that third equation? Multiply by 3. So it'd be 3H2 gas plus, what's 3 times 1 half? 3 halves. Forming 3H2O liquid. So what are we going to do to that delta H? Multiply by 3. Negative 286 times 3 is negative 858 kilojoules. So now that took care of the waters. We're going to add up my 3 reactions to make sure that I manipulated everything correctly before I add up my delta H's as just kind of a final check to make sure that what I did will give me my goal equation. And if it doesn't, then I go and figure out what I did wrong. So, do we have anything that's going to cancel? Yes, what's going to cancel? The carbon and the H2. Those two things are going to cancel. What's going to happen with this? The 2O2 and the 3 halves O2. They're going to add together because they're on the same side of the arrow. They're both reactants, so you end up getting them combined as our reactant. So C2H6, which is a gas. What is 2 plus 3 halves? Is that 7 halves? Good. And then the 2CO2 and 3H2O. So for my delta H's, I'm just going to add up these three values. And that's going to be the delta H of reaction for this combustion. Now, what did I say combustion reactions typically are? Remember, combustion reactions are very exothermic. So you should end up getting a negative delta H for this reaction. What do you get? We'll just go to a whole number. Kilojoules. Negative 1,561 kilojoules. Well, we weren't ignoring them. The delta H for the second and third equations were both to the whole number, so our answer needs to be to the whole number. I don't know who asked that. But remember, when you're adding and subtracting, you're not looking at number of sig figs, you're looking at place value. Okay. Questions on that? That's Hess's law. In your homework, number 1 is a Hess's law problem, and it is a very, maybe not very, it is challenging. It's a little challenging. But if you can do that, you can do any Hess's law problem. If you want practice before you start the more challenging one, remember, you have problems in your guided notes that you should have already done, but you might not have done. You can do those as practice. You can also always redo 21 and 22. Grab like the blank copy from Vision and redo it. Also, in your textbook, at the end of the chapter, we're in chapter 6. Actually, at the end of every chapter, there are problems in the textbook. They're highlighted in blue. If the number's blue, which are all the odd ones, that means the answer's in the back of the book. So there are some Hess's law problems at the back of the chapter in the textbook that you can do the blue ones, the odd ones, so then you can check the answers in the back of the textbook to make sure you're doing them correctly. Okay? Last topic for Unit 3 is the fourth way to calculate delta H of a reaction. It's not the final one. Remember, we're going to do the bond energy one later in the year. But the fourth way to calculate delta H, and that's from the enthalpies of the formation, right? That formula dubbed the Big Mama. Let me write it down for you. This formula is on your formula sheet, so you don't need to memorize it, but you just need to know how to use it. All substances, all compounds, elements, molecules, all pure substances have an enthalpy of formation associated with them. When you form the formation, being formed, okay, synthesized, some compounds, when they're formed, they release energy. Some compounds, when they form, they absorb energy. I'm trying to hold the textbook and not drop it. Most substances, when they form, they release energy. Most substances, when they form, they're exothermic. But there are a few in there that are endothermic. So all elements, ions, compounds have a delta HF value associated with them. If you take the before I said it, what does that mean? Summation, right? If you take the sum of the delta H of formations of all the products and then subtract the delta H of formation of all the reactants, you'll get the overall delta H of the reaction. So it's always products minus reactants. Kind of like when you're calculating delta T, you're doing final minus initial. Your products are what you're ending with, so that's your final. Your initial are your reactants are what you're starting with, so that's your initial. In this problem, I've given you a chart that's a little bit prettier in your packet, but I've given you a chart of the delta HF for the 4 substances in this reaction. Notice that sodium and hydrogen are both 0. What do both sodium and hydrogen have in common? They're both elements. Oh, I like the way you said that. They both have an oxidation state of 0. They're both elements. More specifically, they're elements in what form? Let me tell you this.
Oh,
It
diatomic.
no, not diatomic, because sodium's not diatomic. If I had in this reaction, if I had sodium in the liquid form, it would have a delta HF value associated with it.
And it's
Natural or standard? The state of matter at room temperature. Remember, all of these are. Remember that little degree sign means in the standard state, which is what temperature? 25 degrees Celsius and 1 atmosphere. That's room temperature. So the elements that are in their natural state or their standard state of matter for at room temperature will always have a delta HF of 0. Okay? You need to know that. Because after this problem, you will never again be given the delta HF for an element in its standard state. So if it's not given to you, you need to know that the reason it's not given to you is because it's 0. On the AP exam, they used to give you whole charts of all the delta HF values that you could possibly use for the entire AP exam. And this chart is found in appendix number 4 in your textbook. Okay? And this chart in general actually has more than just delta HF. It actually also has delta G and delta S values for each substance. For right now, we're only using delta H. But they used to give you these huge charts, and you'd have to spend time flipping through them and figuring out everything. Now, they just give you the pertinent information in the problem. Okay? But I still want you to know how to read these charts. So for your homework, it says use appendix number 4. That's talking about the appendix at the back of your textbook. So you'll need to look up the values for your homework, but I don't feel bad about that because you're not timed on your homework. For like your tests, I'm not going to make you spend time looking through charts trying to find your substances and rushing and stress. Okay? So like I said, all of the pertinent information is in the chart here on this problem. So to find the delta H of reaction for this reaction, we're going to take the sum of the products of their delta HF values. So we have sodium hydroxide, which is negative 470. But this negative 470 is for one sodium hydroxide. How many sodium hydroxides do we have? 2. So don't forget to multiply by the coefficients from the balanced chemical equation. So 2 times negative 470 kilojoules per mole plus hydrogen, which is 0. You don't actually have to write that you're doing 1 times 0. I'm going to for the sake of the notes, though. Okay. Minus, always products minus reactants, the sum of the reactants. So we have 2 sodiums. What sodium is delta HF? 0. Plus, we have 2 waters in the liquid state. What is water? negative 286 kilojoules per mole. Gaseous water has a different delta HF value. So now if you're just going to do the math, really you're just doing 2 times negative 470 and 2 times negative 286 and finding the difference. What'd you get? Negative 386 kilojoules per mole. So this overall reaction releases 386 kilojoules of energy per mole of reaction. Right? Questions?
That means it's exothermic.
Yes. Exothermic. Cool. All right, we have 2 more problems and then we're done. Yeah. Yeah. So, anyway, in your packet, number 26 is actually part of the thermodynamics unit, which is a later unit. Last year, this was all one big unit, and then it was chapter 6 and 17 together, and then I'm splitting them for this year. So I accidentally left 26 on there. You can cross that out. We'll do that problem later, but I'll put it in the next packet, in the correct packet. So last 2 problems are 24 and 25. 24 is just like number 23. But I'm going to give you the pertinent information instead of taking the time to look it up in the textbook. So ethanol is negative 278. Ethanol is negative 278 kilojoules per mole. Carbon dioxide is negative 393.5 kilojoules per mole. And water is negative 286 kilojoules per mole. Yeah, because there's 2 of them. Yep. Yeah, this is just these are the values for one of those substances, one of those compounds. So you need to do the multiplication. Why did I not give you O2? Because it's 0, and you need to know that it's 0. Right? So take a few minutes to set up the problem. I'm going to pause it while you do that. Set up the problem and write down your work. Do all that stuff and calculate it. You can check with your neighbors once you have it calculated to make sure that you've done it correctly. Now that you've had a moment to calculate it, setting it up, it should look like this. Technically, it's plus, 3 times 0, but you don't need to actually write that.
Do you think we would see this more in free response or?
Yes. Free response. So when you check and make sure you set it up properly, make sure you do products minus reactants, and you're multiplying the coefficients by the delta HFs for each substance. So when you do that, what did you guys get as your delta H of reaction?
500.
Nope.
Negative 500.
Nope. You should have gotten negative 1,367 kilojoules per mole.
See, I had a decimal.
Okay, shh. Yes. Okay. Okay. It could have been that you just typed it in wrong. I strongly encourage you not to be doing these calculations on your phones and to be doing them on a calculator that similar to one you'll be using on the AP exam or on a test. Okay? Okay. Last problem. Number 25. So the standard enthalpy of combustion to CO2 and H2O at 25 degrees Celsius of cyclohexane, C6H12 liquid, is negative 3,924, and that's kilojoules per mole. We're calculating the standard heat of formation, delta HF, for cyclohexane. So the delta H of combustion for this reaction is given. Negative 3,924 kilojoules per mole. What is combustion an example of, or a type of? Reaction. So that is the delta H of reaction. This is like the answer, and we're solving for one of the components. All right? We don't know this, delta HF. That's what we're solving for. Honestly, the CO2 and H2O are the exact same from the previous problem, the negative 393.5 and the negative 286, and both of these are kilojoules per mole. Why didn't I give you oxygen? Because it's 0, and you know that elements in their standard state of matter have a delta HF value of 0. So in setting this up, you're solving for one of the components, not the overall delta H of reaction. Okay. So take a few minutes. I'm going to pause this while you try this calculation. When you have it calculated, turn to a neighbor, check your answer, see if you got it right, and then we'll check back in just a few minutes. Now that you've had a chance to do this calculation, let's set it up just to make sure we're all on the same track. So delta H is our answer, so negative 3,924 kilojoules per mole. Products minus reactants. Our products are 6 times negative 393.5 kilojoules per mole. And 6 times negative 286 kilojoules per mole. Minus, we don't know the delta HF of cyclohexane, plus 9 times 0. Right? You don't actually have to write the 9 times 0. Again, I'm just doing that for the sake of the notes. So through the power of algebra, you should be able to solve for x. Let me give you the intermediate step just in case you struggled with this. You should have gotten to this point at some point. That's a negative. My negative and my 4 kind of merged together. Let me rewrite that. Negative 4077 minus x. So manipulate, solve for x, and you should get x as negative 153 kilojoules per mole. And that is your delta HF of cyclohexane, C6H12. No, you do not need to include the 9 times 0. Cool? All right, that marks the end of Unit 3.